Hi there, I'm Prof. Joe. I'm a professor for automation and measurement technology, and this is part of my AI-Tutored lecture on measurement technology. And that's the last part of the chapter about alternating currents. Today talking about the power of an alternating current. Okay, remembering basic electrical stuff. We know that our power of an electrical source can be calculated by multiplying voltage times current. For DC currents, that's quite obvious. Now for alternating currents, this changes a little bit because we have some time-dependent voltage and current. So what one can do is doing the integral over u times I dt, and that's it. That's well worth doing. When having the digital signal, it's easy to do it anyways. And you will get the power, and you will get some insight into what happens. Why is that the case? Thinking about a sine or a cosine function for the voltage or the current, such an integral is calculatable. So it's an integral which can be calculated, which perhaps needs some mathematics, but which is calculatable. Now, we get into the problem over here that current and voltage don't need to be in phase. For example, when having a capacitance in an electrical circuit, the voltage applied to that capacitance will load the capacitance, and that capacitance will deload sometime later when no voltage is applied anymore. And that means the voltage falls again, and at that point, the capacitance will exert an additional current. And that changes the current curve, which then indeed gets out of phase with the voltage. That has to be somehow taken into account when talking about those integrals, meaning most of the time you should even use the exponential functions with imaginary parts to do that calculation. And that means we get some complex numbers. Now, to simplify that calculation, for sure, some guys were thinking about that stuff beforehand and told us that the complex power of an alternating voltage is the complex effective value of the voltage times the complex effective value of the current, and that indeed is the effective value of the voltage, the not effective value of the voltage, times the effective value of the current, times the phase between current and voltage. Okay, that's something which can be calculated. So, okay, fine. We can, for example, when having a sine function which we are measuring, we can measure current, we can measure voltage. We see that difference in phase. We see the phase shift. We can measure the peak values. Using the peak values, we can calculate the effective values, and so on and so on. And we get our complex number for the power, which means there's a real part of the power and an imaginary part of the power. Now, for sure, the question arises, what the heck about an imaginary power? That's a good question indeed. Again, same holds for any which current, alternating current out there. We only can see the real part of our current or of our power or whatsoever. What does that mean? That imaginary part is somewhat a help to do the calculations. It helps us to do the calculations. But for sure we cannot directly measure the imaginary parts. How to describe that more decent? Imagine there's your voltage and imagine there is your current. So, voltage, and now we get that current which might be slightly out of phase, having a different amplitude. That is absolutely measurable. You can measure that current, you can measure that voltage, and that will give you real values. Whatsoever, there's a phase in between those values you are measuring. And to get that phase into our equations, we can use imaginary parts. Those phase correlations are incorporated in the imaginary calculus for those alternating currents and so on. Whatsoever, most of the time we are, as I said, only interested in the real parts. Sometimes imaginary parts get important because they will exert real parts in other parts of the circuit. But for now we are talking about simple circuits. So we have that real part of our system, and that's the active power which gets exerted in ohmic resistances, meaning, for example, in a motor, in a light, or whatsoever. There's some power needed to drive the motor, and that's the real part of that thing. On the other hand, there's the imaginary part. That's the reactive power. And that's the power we cannot really use. Why is that so? Think of that capacitance and think of a deloading. That deloading current could be used in some cases, but for those cases it is used, you convert that imaginary part to a real part. And so whenever you don't convert that back, you don't explicitly use a capacitance, the case is that that current flowing from the capacitance will be in counter direction to the current you want to get the system flowing. Meaning you try with your voltage to apply a certain current, and that those capacitance, for example, will work counter to that voltage, to that current you want to apply. And that means those imaginary parts, those reactive powers, are the stuff we don't want to have because we can't use them. They get lost in the system somehow. For complex alternating voltage circuits that don't really get lost, you can compensate for them, but you have to compensate for them. So overall, that's the thing we don't want to have. So it's always sensible to talk and treat capacitances within an alternating current network, because perhaps we can reduce reactive powers, we can reduce phase shifts, we can optimize phase shifts, we can optimally use capacitance and inductance. Okay, now that's for the definition of the power. Some interesting things can be said about that stuff in respect to what that means in reality. First thing is, whenever you want to have a power, for example, you want to drive a motor, you need that motor to be there. If you have a voltage source and you don't connect it to a motor, the voltage source won't exert any power. Okay, that seems to be obvious, but that also implies that the power exerted by a power source heavily depends on the load, on the motor applied to the power source. And that means without load, there's no power consumption. On the other hand, meaning optimizing the load for a certain power source might enable us to use that power source as good as possible. One can do calculations for that. Those are done in the script, which you can use indirectly using that AI-Tutored link below. And those adapting of power and load most of the time means you get the maximum power out of the system when the internal resistance of your power source equals to the load you apply it to. Sometimes that's the thing you want to have. For example, when there's a wind generator generating power, you want to get all the power out of that generator. So you try to adapt that. Sometimes you won't care about that. For example, when driving the motor, the most essential part is that the motor drives at the right speed. You won't care about the power really consumed. You don't want to use your power source as optimally as possible, but you want to have that motor to drive at that speed you want to have it. Meaning for those cases, you're only interested in a power source which has enough power to drive the motor in any circumstance. And now, flipping the side around, when having a generator, you're not interested in a certain motor having a certain speed, but you're interested to get all the power out of the generator the wind produces for you. For example, for that wind generator I was talking about. That's an important fact when talking about power. Okay, moreover, how to measure that stuff. There are special measurement devices which measure the current and the voltage at the same time. They apply at this point over here. So most of them convert your signal into a digital one and integrate over time and get you the power. But important thing is they have two plugs, so-called. You measure your current and you measure your voltage at the same time to know the power which is exerted in a system. There's another way to get to know the power, because we know our ohmic law, which connects voltage to our current and to the resistance, which tells us there is perhaps a way to calculate the power in another way using that. So R would be the load you apply to the system. So when you know the load, it's enough to measure current or voltage to know the power, but you need to know your load. And often, for example, when driving a motor, which load differs depending on the speed, you have to measure your current and your voltage at the same time to get a real insight into the power consumed of the system. Okay, that's enough for a basic knowledge about alternating currents. Next chapter will be about oscilloscopes. Why? Because we need to look at that alternating currents, at arbitrary signals changing over time. Hopefully you enjoyed that stuff. See you next time.